So in the last few lessons, you've learned to write ground state electron configurations. And you can see from the image that I have here at the start of this lesson that my interest at this point is to connect electron configurations back to the periodic table. This is an exciting moment. We've been building to this for a little while now. You know that chemistry is organized using the periodic table as a sort of graphical organizer. And you know that the elements are organized in terms of their atomic number. So hydrogen has 1 proton, helium has 2, lithium, beryllium, boron, et cetera, et cetera. Up to this point, that's what you know about the periodic table, and you know the names of the groups and the names of the periods and things like that. But what you don't know yet, although you might be starting to guess, is why it has such a bizarre shape. And so in this unit, we're finally going to reveal the shape of the periodic table, why it has this unusual shape that's higher on the 2 outsides and shorter in the middle, and then these 2 long bits that stick out at the bottom. It's all related to electron configurations. It's all related to the number of electrons that can occupy each of the shells. So you know, for example, that the N is 1 shell consists only of 1 orbital, the 1s orbital, which means a maximum of 2 electrons can fit into that first atomic orbital. If we look at the first period of the periodic table, we see that it contains precisely 2 elements, hydrogen and helium. Now, why is that? It's because the ground state electron configuration of hydrogen is 1s1. The ground state electron configuration of helium, 1s2, the closed first shell. Now, helium happens to be located on the far right of the periodic table. We'll come back to that later. Sometimes people will put helium in different places, or they'll put hydrogen more likely in different places on the periodic table. But for symmetry purposes, most people put hydrogen on the far left, helium on the far right, and also because that then has the most similarity with the elements that come under it, as we'll see in the next few minutes. So there are 2 elements in the first period corresponding to the fact that 2 electrons can occupy a 1s atomic orbital. Now, if I label the second period as n is 2, it's going to start to become immediately obvious to you why there are 8 elements in the second period. 1, 2, 3, 4, 5, 6, 7, 8. 8. Now, which atomic orbitals are possible in an n is 2 shell? The 2s atomic orbital and the 3 different 2p atomic orbitals. So a total of 4 atomic orbitals in the second shell, which means a total of 8 possible electrons. And I just showed you that there are 8 elements in the second period of the periodic table. Those correspond to all of the possible electron configurations with valence electrons in the second shell. So I labeled the top of column 1A as S1. You'll see why in a minute. I'm going to label the top of column 2A as S2. And then I'm going to go all the way over to the right side of the periodic table, so staying in the main groups. I'm going to call 3A P1, 4A P2. You'll see the pattern, P4, P5, and above the noble gases here on the far right, I'm going to write P6. And we already talked in the previous lesson about these noble gases because they contain filled shells. So the ground state, I hit the bar on the side. The ground state electron configuration of helium is 1s2. For neon, the noble gas immediately under it, it has a filled second shell, so 2s2, 2p6. But you're already seeing a shared chemistry between helium and neon in that they both have completely filled shells of atomic orbitals. Now, if we continue down the periodic table, looking at the n is 3 period, again, you see that there are 8 elements in the main groups of the third period. Again, those correspond to elements that have valence electron configurations of S1, S2, and then over here, the S2 is assumed because it's already filled, but aluminum has a ground state electron configuration that's 3s2, 3p1. Remember, the p is the next highest in energy, all the way through to argon, which has filled 3s and 3p atomic orbitals. Things become interesting now when we move to the N=4 period. So potassium and calcium, that's easy. You've seen already in the previous lesson, the potassium has a ground state electron configuration that's the argon core followed by 4s1. Similarly, calcium is a 4s2 ground state electron configuration. And then scandium, the B period, the B group, has an electron configuration which is D1. Titanium is then D2, and we move through the D block, right? This part of the periodic table is called the D block because its highest energy electrons are in valence orbitals that are D-type orbitals. How many D orbitals do we have in any given period? 5, which means a total of how many electrons? 5 times 2, or 10. So how many columns should we expect in the D block? Precisely 10. And if we count them up between scandium and zinc, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Precisely 10 columns, corresponding to the different electron configurations in which the valence electrons are in the D orbitals. Now, it's worth noticing that this first D block period is in period 4, but the atomic orbitals that are occupied by these elements are actually the 3D atomic orbitals, not the 4D, because the 3D is higher in energy than the 4s. So that's why we have this sort of cave or valley in the middle of the main group, because there's a couple of periods that just don't have any D orbitals. And so although titanium, for example, has a ground state electron configuration of a closed argon followed by 4s2, 3d2, not 4d. The period, or the principal quantum number of the D orbital, is always 1 lower than that of the main group orbitals around it. And then the last part of the periodic table that we haven't talked about is these 2 rows down here at the bottom. Technically, they go into this spot that's left blank over here, but that would then make the periodic table really, really wide and would make printing not particularly convenient. So we typically put those at the bottom of the table. Those are the so-called F block elements. And so how many F block groups do you expect? How many F atomic orbitals can a particular atom have? Precisely 7. If each of those orbitals is occupied by 2 electrons, there are 14 possibilities for organization of electrons into F orbitals. If we count up these columns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I got a 15th here. That's a bit weird. Why? Because I didn't put anything up here. So I nicked one off the D. Different people draw this in different ways. Sometimes people put the lanthanum and the actinum here and think of it as D1. And then at cerium, they start with F1. But either way, if you add it all up, we've got 10 in the D block and 14 in the F. We're not going to worry too much about the F block elements in this particular course. You don't find them coming up in the types of engineering applications that we're going to be considering. F block elements are often involved in nuclear chemistry, and that's a relatively specialized area that most of you are not going to work in. So we're not really going to be working with these F block elements. So let's take a look at writing ground state electron configurations of 2 elements in the same group to see how being in the same group naturally means that you have similarities in terms of your ground state electron configuration. So let's start with carbon. Carbon's in the second period. It's in group 4a. So that means it's a helium noble gas core followed by 2s2, 2p2. It has 4 valence electrons. 2 of them fill the 2s orbital, and 2 of them singly occupy 2 different 2p orbitals. Now, we can also look at the ground state electron configuration of silicon. Silicon, if we go back to our periodic table for a moment, is immediately under carbon in period 4a, but in the 3rd period. So for its ground state electron configuration, it's a neon core. Neon is the noble gas at the end of the 2nd period. 3s2, 2p2. Exactly the same sort of arrangement, s2, p2, as what we see in carbon. And that means that these 2 elements will have a lot of similarities in terms of their chemistry. And that's why they're paired together vertically in the same group in the periodic table. A group of the periodic table has a shared valence electron configuration. Because, as we said before, the valence electrons are where the action is. It's where chemistry happens. So if you know the valence electron configuration of one element, and you have another element with the same valence electron configuration, you'd predict that they're going to undergo similar types of reactions. So what we've learned in the last few minutes is the order in which the atomic orbitals fill can be predicted immediately using the periodic table. There's absolutely no reason to memorize the order in which atomic orbitals fill because you can read it straight off the periodic table. So let's go ahead and practice another element. Let's take a look at manganese. We haven't been working with our D block metals yet, but let's look at manganese. Manganese is in the 4th period. It's in the D block, so it's got occupied 4s orbitals, and then in the D block, it's 1, 2, 3, 4, 5 elements into the D block. So what's its ground state electron configuration? Its ground state electron configuration is argon, since that's the filled noble gas at the end of the 3rd period, followed by 4s2, and then remember the D is always 1 lower in terms of principal quantum number, so 3d5. So you're now in a position to write a ground state electron configuration for almost any element you can find on the periodic table. We don't need to go through and memorize them. We don't need to memorize the orders the orbitals fill. We can just read all of that information off of the periodic table. And that's one of the many reasons that the periodic table is so extremely powerful. Now, I'm an inorganic chemist, which means I study all the stuff on the periodic table. And inorganic chemistry, we often like to say, is all about the exceptions. There are exceptions. So I just want to draw your attention to these exceptions for the next few minutes so that you'll notice them when they come up. So we just wrote the ground state electron configuration for manganese, and that was easy. But let's look at the element next to manganese, and that's chromium. So let's go back to our periodic table for a moment, and let's look at chromium. That's 1 to the left of manganese. So we might predict that it's an argon core, 4s2, 3d4. That would seem reasonable. That's not what it is. It turns out that actually the ground state electron configuration of chromium is an argon core, a half-filled 4s, and a half-filled 3d. You couldn't possibly have predicted that. But it turns out the energies of the 4s and the 3d are so similar and are actually changed by whether electrons occupy them or not, so that these sort of special half-filled arrangements are more stable than having the filled s and 4 in the d. So quite often in that D4 column, you'll see irregularities, and also in the so-called D9 column. So another example of irregularities is copper. So copper is right here in period 1b, which we might call D9. You might predict that it's 4s2, 3d9. That would be wrong. In fact, it's 4s1, 3d10. So this same arrangement where the D becomes completely occupied because a half-filled 4s happens to copper that happened to chromium. So I don't want you to go through and memorize all of these things. I just want you to keep your eyes open and notice it when it happens, because whether electrons are paired or not has huge implications on the chemistry, and also on the electrical and magnetic properties of a material or an element. So we've now come to the end of our series of lessons in the introduction to sort of quantum mechanics, which is a huge amount of material. I can understand if you're feeling a little bit overwhelmed. So I just want to take 1-2 minutes to summarize what we've learned thus far in the simplest possible terms. So far you've learned that as a result of their wave character, electrons occupy atomic orbitals, which are basically just wave representations of the probability of finding an electron at a place in space. You've learned the shapes and the energies of those atomic orbitals, and you now know how to predict which orbitals are occupied for any given element. So you're able to use all of this information that you've learned from quantum mechanics, these abstract physics ideas, to predict the arrangement of electrons in any element of your choice using the periodic table. And from that information, as we'll learn in the next several weeks, you can learn something about the chemistry of any element. Because as I said, the chemistry of an element is directly related to its valence electron configuration. So this is a good time to pause, to pat yourself on the back for having gotten through a lot of material, but also to stop and solve some problems to make sure you understand what's happening before you move on to the next set of lessons.